This is Lecture 2 of Module 4 from the book Problem Solving Guide for Mechanics and Thermodynamics, Circular Motion. In Lecture 1 for this module, we derived the fact that a particle moving in a circle of radius r at constant speed, v, has an acceleration towards the middle of v squared over r. If there is an acceleration towards the center of the circle, there must be a net force towards the center of the circle. This module introduces no new forces. There are no new forces. Some people like to talk about centripetal force, but it's not a force. When a car travels around a curve at constant speed, what force or forces producing the acceleration? If the road is flat, it must be the frictional force between the tires and the road. If the road is banked, it's probably a combination of the frictional force and the inward component of the normal force. This is why curved roads are banked inward, to provide the inward force necessary to produce the acceleration. So let's consider the forces on a car traveling through a banked turn at constant speed. So there's a top view of the curve, and here's a side view of the curve. In this picture, the car is heading straight into the page around a curve. So we have gravity, you have the normal force, perpendicular to the surface, normal to the surface, and we have the frictional force. Now, if the car is not going super fast around the curve, if it's going really fast, the frictional force is going to be inward. If it's going really slow, you can imagine that the frictional force would be holding the car up if the car is going slow and it's banked substantially. Usually the frictional force is inward because people drive fast, and you need more force toward the middle because you have more acceleration towards the middle of the circle. If these three force vectors are added, which way will the result point? There's the normal force, there's the gravitational force, and there's the frictional force. There's the net force, which is not a force on the car, it's the result of the forces on the car. And that's to the left, which is in the direction of the acceleration, towards the middle of the circle. That's the way the net force has to point, toward the acceleration. Now it's tricky because the normal force changes with the speed of the car. The faster you go around the turn, the bigger the normal force grows. You need it to keep you going in a circle. If you're on a roller coaster and you go into a dip at a high speed, the seat at the bottom really has to push up on you because you have a big acceleration upwards. V squared over r is upwards towards the middle of the circle when you go through a dip. If you're a passenger in the back seat of the car and the driver's flying around a turn, you need a force to keep you going in the circle. And you could grab onto the door handle. If it's not too fast, the friction in the seat might provide it. Or leaning onto the passenger next to you. So let's do a problem. Here's a video clip of Deanna Price throwing the hammer 80.3 meters recently to break the American record and qualify for the Tokyo Olympics. Let's see how this works. It's a 4-kilogram ball. That was certainly circular motion. You can see the second place person threw at 74 and she just threw at 80.3. The woman's hammer has a mass of 4 kilograms. The steel cable it's attached to, 3 feet 11 inches long. It looks like this. Swing it around in a circle really fast and let it go. Let's try to estimate the tension in that cable just before she released it. So from kinematics, projectile motion, we can estimate that the speed of that hammer was about 30 meters per second when it was released, which is about 67 miles an hour. And we can look at a picture of her and try to estimate the radius of the circle in which the hammer is moving when she releases it. 2 meters is not a bad estimation. There's gravity and tension on the hammer, but the tension is supplying the centripetal force. Tension is causing that hammer to move in a circle. And as soon as the tension goes to zero, when she releases it, the hammer travels in a straight line under the influence of gravity. So there's the tension. Tension is MA towards the middle, which is MV squared over R. And if you calculate this, it's 1,800 newtons, which is about 400 pounds. So she's pulling inward with the force of about 400 pounds on that thing when she lets go. That was fun, but we had to do a lot of estimating there. Let's do one with a little bit more precision. The Cleveland Velodrome, just south of downtown Cleveland, 166-meter oval track with turns that have a 15-meter radius at the black sprinters line. They're banked 50 degrees up from the horizontal. Here's a picture of the turn. That is the steep turn. Olympic velodromes, which are bigger, they have turns banked inward only at 42 degrees because the radius of the turns are larger, and you don't need so much normal force. If the track is small, you need a lot of normal force because the radius is small. Who wants to try that? Looks like fun. So, a rider travels along the black line at the bottom, that's the sprinter's lane, at a speed of 20 miles per hour. Constant speed of 20 miles per hour. What's the magnitude and direction of the frictional force on the tires from the track? Start with the good diagram. There's our diagram. The forces on the rider and the bike are gravity downwards, straight downwards. The normal force is normal to the surface. There it is. Now the frictional force depends on how fast the rider's going. If the rider's going slow, the frictional force is going to hold them up. If the rider's going really fast, the frictional force will actually be downward, down the plane, down the hill. You can imagine somebody going 40 miles an hour around that turn, and if frictional force is suddenly turned off, they're not going to go down the track, they're going to go up the track. But 20 miles an hour is slow, so the frictional force is up the track. So now we have to consider the coordinate system. Those are our three vectors. And as before, as always, we should put the x-axis in the direction of the acceleration to minimize the amount of math we have to do, and that's the goal in physics all the time. Let's minimize the amount of math we have to do. So the acceleration is towards the middle of the circle in which the cyclist is moving, which is to the left. So here's our coordinate system. There's x, there's y. I'm going to redraw it without just considering the rider as a point mass. We're going to break up those forces, the normal force and the frictional force, into horizontal and vertical components along the x and y axes. For this, we need the angle that the normal force makes with the coordinate system. So the hill is 40 degrees, the bank is 50 degrees, so this angle is 40 degrees, which means this angle is 50 degrees, right there. So now we can break up the normal and the frictional force into their components with trigonometry. The magnitude of the vertical and horizontal components of the normal force, Fn sine 50. For the x direction, that's the opposite side of the 50 degrees. And the y direction is cosine 50 degrees. And let's put these on the force diagram. So we're going to replace this normal force vector with its components. See how that works? We had that, and we say we want to do x and y direction because of the acceleration, and we split it up like that. We can leave the angles out. We can put them in later. The horizontal and vertical components of the frictional force. The x is cosine 50, and the y is sine 50. And let's put those on the diagram as well. So we're going to replace this vector at 50 degrees with two components. Now we can write the force equations in the vertical and horizontal direction. Because we were judicious in choosing our axes, the sum of the forces in the y direction is 0. All of the accelerations in the x direction. So the forces balance in the y direction. So in the vertical direction, the y direction, the normal force in the y direction plus the frictional force in the y direction balances the force of gravity. So the normal force in the y direction and the frictional force in the y direction are holding up the bike and the rider. Normal force components, the components in the y direction balance mg. In the horizontal direction, we have the normal force minus the frictional force. is ma in the x direction. Well, wait a minute. The acceleration, the speed's constant. What's the acceleration? It's v squared over r, right? Going in a circle at constant speed, v squared over r towards the middle. Now we cannot relate Fn to Fr. You might want to say frictional force is mu static Fn, but we don't know that if it's the maximum. So if the cyclist is not slipping, we can't use mu k, and we can't use mu static unless we know it's the maximum force. So these are independent variables. They have two unknowns. In the vertical direction, we have putting in the angles. In the horizontal direction, putting in the angles, we have Fn sine 50 minus Fr cosine 50, mv squared over r. That's ma. Usually, we have a nice equation, not two ugly ones. Both of these are ugly. We just got to pick one. Let's start with the equation in the horizontal direction. We have Fn sine 50 minus Fr cosine 50 equals mv squared over r. And our speed's in miles per hour, 20 miles per hour. We have to convert that to meters per second. So let's do that. 1 hour divided by 3,600 seconds, that's equal to 1. The numerator and the denominator are the same. 1609 meters equals 1 mile. That's another fraction that's equal to 1. So we multiply 20 miles per hour by 2 fractions equal to 1. This is the same as 20 miles per hour because we just multiplied by 1 twice. It's just expressed in different units. So 8.39 meters per second, 8.939 meters per second. Now we have everything but the two unknowns, Fn and F friction. So there it is. In problems like these, I like to calculate what the acceleration is, just because I'm curious. What do you think the acceleration of the rider is? It's 5.3 meters per second towards the middle of the circle, which is more than half a g. More than half the acceleration due to gravity, which is significant. You certainly feel it. The pressure on the tires has to be big because the bike is really getting squished into the road when it goes around a turn like that. So now we have, plugging in all the numbers, ma is 426.2 newtons towards the middle of the circle. And that's all we can do with that. We need another direction because we have two unknowns, one equation. So in the vertical direction, we have the two upward components balancing gravity. We can put in the angles, the numbers for the sine and cosine, and mg, and we get this. We can solve this for Fn. So we subtract Fr times 0.766 from both sides and then divide by 0.6428, and we have this expression. So now we can take our expression for the normal force and substitute it into the equation for the horizontal direction. There's the equation from the horizontal direction, and we're going to substitute for Fn. And there it is. That's what we have for Fn. And now we have one equation, one unknown. So we just multiply out the left-hand side to get this. We combine the two Fr terms. And we subtract 953.7 from both sides. And we can get the frictional force, 339 newtons, which is what the question asks for. And it's up the track. Let's calculate Fn so we can check our answer. So we had an expression for Fn. We can plug in what we had for the frictional force, and we get the normal force is greater than the weight. Even though the track is banked significantly, the normal force is greater than the weight of the bike and rider. So here's the original force diagram. When drawn to scale, if we're careful, the sum of those three vectors should point towards the center of the circle because that's the direction of the acceleration. So let's do that. Here's Fn. Fr is perpendicular to that. Fn's perpendicular to the track. Frictional force is along the track. And now we got to add gravity, doing the head-to-tail method. And voila, there's the normal force. There's the net force. And that's the sum of the three forces. It's inward, towards the middle of the circle, as it must be. And it was 426 newtons, and that looks like it's to scale. Gravity's 800. F net's 426, that's 339, that's 841, all looks good. But let's check it again. Let's get all the components. The magnitude of each of the components and put them on the force diagram. Gravity is easy, it's already vertical, there it is. The component to the normal force, we're just going to plug in for what the normal force was, 840.9 newtons, and we get those two components. Let's put those on the diagram. There they are. And now friction was 339 newtons. We're going to get the x and the y components. The x is 218 back, and the y is 260 up. So let's put these on the figure. Now we can look at this diagram and think. Let's see, what's the upward force, 260 and 540? 260 plus 540, what's that? Ooh, it's 800. Okay, so there's 800 up and there's 800 down. Those balance. There's no net force in the y direction. As we know, there must not be. In the x direction, we have 644 towards the middle, 218 back, and 644 minus 218 is 426, and that's MA. Okay, your turn. Do some problems. Not some, many. Do many problems. Get to work.